In this tutorial, we're going to be going over writing the Lewis structures for a molecule that has one central atom and is not having any octet-rule exceptions. So there's two different methods I'll be going over in this tutorial of how to draw these structures. One of them is called the connect the dot method, and the other one is the skeletal structure method. The connect the dot method is faster and easier, but it does not always work, especially when you're dealing with an ion, while the skeletal structure works every time, but it is a few more steps. So let's first look at an example that we're going to solve using the connect the dot method. The first step is, if we're given a formula, to go from the formula to the structure, we first need to know which atom is the central atom. These are for questions where we're specifically told there's only one central atom. The central atom is the one that can make the most bonds. So to determine which one can make the most bonds, we're going to look at the Lewis structure for each atom separately. And if there are no octet-rule exceptions, we can only form bonds to an unpaired electron. So I'm going to go ahead and look at this first question and apply that first rule before we go on to the next rule. So the sample problem I've got here is drawing the Lewis dot structure for formaldehyde, which is CH2O. So I'm going to draw the Lewis dot structure for each of these atoms separately. First we have carbon. Carbon is group 4A, so it has 4 valence electrons. There, to do the Lewis dot structure, you put 1 electron per side before you pair up. In the carbon's case, we ran out before we paired it up. Then we have 2 hydrogens. So hydrogen is group 1A, so it has just 1 valence electron. Then oxygen. Oxygen's group 6, so it's going to have 6 valence electrons. So 1, 2, 3, 4, 5, and I'm going to put the 6th one on the opposite one. So we now have 6 valence electrons. Looking at these structures now, we can form 1, 2, 3, 4 bonds to carbon. Hydrogen we can only form 1 bond to. Again, you can only form a bond where there's an unpaired electron. You cannot form one to an empty spot. Oxygen, you cannot bond into a pair of electrons, so these pairs of electrons we're not going to touch, but we can bond to the unpaired. So oxygen is going to have a possible 2 bonds versus hydrogen 1 bond and carbon 4 bonds. Note that because carbon almost never does anything against the octet rule, carbons almost always will have a total of 4 bonds in a molecular structure. So therefore, carbon with 4 bonds, that's going to be our central atom. The other atoms, in this case 2 of these hydrogens and oxygen, are going to be called terminal atoms. If you think about the terminals at an airport being outside or around the outside of the building, that's what we mean by terminal atoms, those that are around the outside of the center. So now that we've identified which one is the central atom, the next one is we're going to connect those terminal atoms to the central atoms by connecting the dot, meaning connect the unpaired electron to unpaired electron. So I'm going to draw carbon in the center. Dot, 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 dot. Hydrogen. Hydrogen. And each of them have 1 dot. And then over here, the oxygen. 1 dot, 2 dots, 1 dot, 2 dots. So connect the dot. Dot to dot. Single unpaired electron to single unpaired electron. There. Now notice in this structure, at this point, we have unpaired dots left. There's an unpaired dot on carbon, and there's an unpaired dot on oxygen. So if we have any unpaired electrons, we're going to use them to make double or triple bonds. So I'm going to take that electron here, and I'm going to move it here and here so that I can make a second bond, like that. So then the final structure has carbon in the middle, hydrogens. It doesn't really matter which sides you do it to. You can do it top and bottom like that, and then have the oxygen out to the side with a double bond going out to the oxygen. Know that the oxygen still has 2 lone pairs. It's important to still show those 2 lone pairs because they are part of the structure. So there's our completed structure for formaldehyde. Let's try another sample problem. Draw the structure for phosphorus trichloride PCl3. So again, we're going to draw the Lewis dot structures of each of them individually to determine which one will be the central atom. Phosphorus is in group 5A, so it will have 5 electrons around it. 1, 2, 3, 4, 5. Chlorine is in group 7A, so it will have 7 electrons around it. 1, 2, 3, 4, 5, 6, 7. So phosphorus can make 1, 2, 3 bonds, while chlorine can only make 1 bond. Therefore, phosphorus will be our central atom. So let's draw our phosphorus in the center and put the chlorines around it and line it up so that the chlorine is on each side, that you have a unpaired electron on phosphorus. So we'll put a chlorine here and line up its unpaired electron. Don't forget its lone pairs that are already paired up. Another chlorine. And the last chlorine. And then connect the dots. Let's double check that we didn't use too many electrons and that everybody has an octet. So the number of electrons are available for bonding is the total number of valence electrons. Phosphorus being in group 5 gives us 5 valence electrons. Chlorine being in group 7 gives us 7, and we have 3 atoms of chlorine. So 21 plus 5, we have 26 electrons. Let's count to make sure we still have 26 electrons in our structure. Lone pairs are 2 electrons, and the bonds are 2 electrons. In all of these structures, you should not end up with an electron sitting by itself that is either not paired up with another electron or not involved in a bond. An unpaired electron is something called a free radical, which is very high energy and unstable. And in these types of problems, we will not end up being asked to do one of those structures. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we have our 26 electrons. Check. Next, we're going to double check that everybody has an octet. By octet, we mean that everybody has access to 8 valence electrons, except for hydrogen only wants 2. The idea being that everybody wants to be like the noble gas that's closest to them. And all of the noble gases have 8 valence electrons, except helium, which only has 2. Hydrogen's closest noble gas is helium, so it only wants 2. But everybody else is going to want to have 8. So, looking at the chlorine off to the side here, a lone pair of electrons belongs to it, so it has 2, 4, 6, and then the lone or the pair of electrons in the bond are also available to it. Because this is a covalent bond, it has access to both electrons. So there's the 8 electrons. The other 2 chlorines are all mirror images, so they'll also each have 8 valence electrons. Now let's look at phosphorus in the center. It has 2 electrons that belong just to it, and then it has 3 bonds that it shares with the chlorines, each that have 2 electrons. for a total of 8 valence electrons. So the octet rule is satisfied for all of the elements in this structure. In some cases, the connect the dot method won't work. This happens if you are not obeying the octet rule, but it can also happen in some cases where the number of electrons that an atom would normally start with as far as its valence electrons has changed because the overall molecule has a charge. A charge is a difference of number of electrons compared to the number of valence electrons you started with. So if a molecule has a charge, we call that a polyatomic ion, and we have to adjust the number of electrons in our structure. Negative charges mean you've added electrons, and positive charges means you remove electrons. In these cases, it's easier to use the skeleton structure method instead of the connect the dot method. So let's go ahead and do the steps of this on the NO2 plus ion down here. So the first step is to count the total number of valence electrons in the formula. This is going to be your bank of electrons and should be an even number. So nitrogen, being group 5, has 5 valence electrons. Oxygen, being group 6, has 6 valence electrons, and we have 2 oxygen atoms. Then that positive charge means that we have removed an electron. So we're going to subtract 1 from our bank here. So we have 12 plus 5 minus 1. We end up with 16 electrons. A hint is that, again, if you end up with an odd number of electrons, then that means you would have an electron that could not be involved in a bond or in a lone pair, and you're back to the free radical issue. So make sure you end up with an even number of electrons for these questions. So 16 electrons are available, which means we have to make sure we use exactly 16 electrons. We can't leave any electrons unused, and we can't use more electrons than we have in our bank. Step 2 is to draw the skeletal structure, and that means we're going to put our central atom in the middle and connect the terminal atoms just with a single bond. After we're done with the skeletal structure, we need to update how many electrons are left in the bank because we already spent 2 electrons forming each bond. So for our structure here, we're going to put nitrogen in the center, and oxygen will be our terminal atoms due to the same reasons that we did in the last problem, determining which one should be the central atom. Nitrogen and then oxygen, oxygen, connect it with these lines. This is what we call our skeletal structure because it's just the skeleton of the structure, bare bones minimum connecting these atoms. Now, because we had 2 bonds to make our skeleton, we need to subtract 2 times 2 or 4 electrons from our bank. So now we're down to only 12 electrons left. Our next step is to add the electrons in pairs to each of the terminal atoms to complete their octet. We take care of the terminal atoms first. So everybody wants 8 except hydrogen wants 2. So each of these oxygens are going to want 8 electrons. They currently have access to 2 because of that bond, so they need 6 more, which means each of them is going to get 3 pairs. So 2, 4, 6, 2, 4, 6. So we've used up 6 times 2 atoms, 12 electrons. At this point for this molecule, our bank is empty. Anything we do from this point on cannot cost us any new electrons, but we can still move around electrons if we need to. If we had any extra electrons at this point, we would put them in pairs on the central atom, but we don't for this example. So we're going to move on to step 5. If any atom still does not have an octet, we're going to move a lone pair of electrons to form a double or triple bond. Looking at our structure now, our nitrogen atom in the center only has access to 4 electrons, so it does not have an octet. So we're going to move a lone pair to make a second bond here. Now it has access to 6 electrons, so still not quite an octet. So we're going to move another lone pair. When we move these lone pairs, it still needs to be connected to the atom it was originally with. Otherwise, that atom would no longer have an octet. So we're just going to move it to being bonding that atom towards the central atom. Now our new structure looks like this. Oxygen double bonded to nitrogen. The oxygen still has 2 lone pairs. And on the other side, another double bond to the oxygen, and that oxygen also still has 2 lone pairs. Now everybody should have an octet, and we should still have a total of 16 electrons. The last step is that because we have a charge, we need to show that charge in the structure. Otherwise, it looks like this structure doesn't have the right number of electrons. We cannot just put a plus anywhere on the structure, though, because then it's not clear whether the positive charge is on an atom or on something else. So we're going to put this whole structure in brackets and put that positive charge on the outside. And now our Lewis structure is completed. One more thing to consider is that sometimes when we're making these double or even triple bonds, we'll end up with more than one possible structure that satisfies the octet rule. This just happens if our double bond could be in one place or another, or even if we could replace it with a triple bond on one side and a single bond on the other. In this case, how do we tell which is the correct structure? The best structure will be the one that minimizes something called the formal charge. So we want the smallest possible formal charges, if possible, formal charges of just 0. So the formal charge is basically what would the charge be on that atom if we broke the bond. So if we broke a bond and the atom only got to keep 1 electron from each bond, we can calculate it by the number of valence electrons minus the associated electrons. So for any atom, the number of valence electrons is just going to be its group number again. Associated electrons are what electrons it would still have once those bonds are broken. Let's consider the scenario here of the ion oxygen, nitrogen, and carbon, OCN minus. So when we draw the structure, we end up with 3 possibilities that all have the correct number of electrons and give all 3 atoms an octet. One possibility is to have a triple bond to the oxygen and a single bond to the nitrogen. Another possibility gives a double bond out to both the oxygen and the nitrogen. Note that we still put carbon in the center because it can form more bonds than oxygen or nitrogen. The third possibility is a single bond to the oxygen and a triple bond to the nitrogen. So let's go ahead and figure out what the formal charges are here. On the oxygen atom for the first structure, oxygen starts with 6 valence electrons because it is in group 6. If I broke all of its bonds and it only got to keep 1 atom per bond, it would have 3 plus 2, or 5 associated electrons. So 6 minus 5 would mean a plus 1 formal charge. Carbon in the center, if it broke all of these bonds, would have 1, 2, 3, 4 valence electron or associated electrons. Carbon starts with 4 valence electrons minus the 4 associated, 0. Carbon should always end up with a formal charge of 0 for most structures. Now nitrogen. Nitrogen is in group 5, so it starts with 5 valence electrons. This nitrogen has 3 lone pairs for a total of 6 electrons that belong to it, plus 1 more here that it would get if that bond broke. So a total of 7 associated electrons, which gives nitrogen a formal charge of -2. This is probably not going to be a good structure because we have +1 and -2 here. Let's try the structure where we make both sides a double bond. So this oxygen, again, starting with 6 valence electrons, its number of associated electrons in this structure is 2, 4, and then 5, 6. So oxygen here ends up with a formal charge of 0. Looking better. Carbon still 0. Nitrogen on this side, 5 valence electrons minus, now it's got 2, 4, 5, 6. So -1. And then carbon's still 0. This last possibility now, the single bond is on oxygen and the triple bond is on nitrogen. If I have the single bond on oxygen, it has 2, 4, 6, 7 associated electrons for a -1 formal charge. Carbon is still 0. Nitrogen now has 1, 2, 3, 4, 5 associated electrons, so now it has a 0 formal charge. So out of these 3 structures, we know it's definitely not going to be that first one. But then what about these next 2? Both of them have 2 formal charges of 0 and 1 formal charge that is -1. It's impossible to have all zeros for formal charges when you have a charge on the molecule, because the sum of the formal charges has to add up to the sum or the charge on the molecule. But the question is, who should get the negative charge, the nitrogen or the oxygen? And for this case, it's going to be the oxygen should get the negative charge, not the nitrogen. Why? Because oxygen is more electronegative than nitrogen. Because it's more electronegative, it has a stronger pull of electrons, and it would be more satisfied by having that negative formal charge than a nitrogen would. So out of all these structures, the third one is actually going to be our best structure. So this was how to draw a Lewis structure with one central atom, no octet rule exceptions, just simple small molecules.